Okay, I am recording now. So we're starting the section 5.1 notes. We're talking about extreme values of functions. And let's define absolute maximum. Absolute maximum, as the name implies, is the highest y value in a specified domain. So if you have a domain, like say maybe you're only looking from 1 to 4, or from like maybe 2 to 10 or something like that, you want to find the highest y value. That's called the absolute maximum. So graphically, let's say I start a graph at like x equals 1 and at x equals 4. And say it does some sort of funky things like this. That's my absolute maximum. It's the highest point. There you go. The absolute minimum is going to be the lowest y value for a specified domain. So let me do another graph. Let's say I have a graph that does something kind of like this. It dips down, then kind of goes up, and then ends right here. That's my absolute minimum. It's the lowest y value. Okay. More formally, and it's a little weird, when you have a specific domain, f of a is the absolute maximum on your domain if only if f of a is higher than any y value for x. So this means f of a is higher than any y value in your domain. And so if I call this like a right here, let me change colors for a bit of contrast. If I call this a right here, that of course would be f of a. Great. There you go. So f of a is higher than any y value within our domain. And then likewise, if I call this like b here, and that's f of b, then f of b would be lower. So you write the same thing, but you say f of b is lower than any y value in your domain. That would be an absolute minimum. And there's going to be quite a bit of theory, just so you know. In fact, probably a proper title for this section would be called the extreme value theorem, because we are going to talk about that at the bottom of this page here. Now, there are some things we have to assume when finding absolute mins and maxes. And when I say absolute, what I mean by that is like just the highest possible point that you see, or absolute minimum, the lowest possible point you see. So let's look at example 1. So here, our domain is not restricted. The first graph, it's from -infinity to infinity, so it goes on. So actually, it should be arrows here. This goes on forever. Obviously, this is y equals x squared. And these are already sketched, so don't worry about that. That's been done for us. But we are going to state the absolute max and absolute mins if they exist. So if this goes on forever, so we call this an open interval. We call this an open interval. So if it goes on forever, this doesn't, there's no left endpoint, there's no right endpoint. Just by looking at this, there's no absolute max. There's none. Because it's just these point up forever. I don't know what the highest point is. I've got no idea. The absolute min, however, I do know. It's 0. And just so you know, when you state this, you state the y value, not x. If they want the x value at the minimum, you'd be explicitly told to do so. Like say, oh, give me the x coordinate at the absolute min. Fine. But when they ask for the absolute min or absolute max, they want the y value. Okay, question in the chat. If the ends of the graph point up forever, you could say, okay, so great question. Can we say it's positive infinity? Sure, you could. That's fine too. Or positive infinity. I mean, infinity is kind of an abstract idea, like it's a number that just goes forever. But sure, you could say that too, not a problem. Now, what if I do close the interval? So this is closed now, from 0 to 2. In fact, let me draw the endpoints right here. And let me just connect those two. So do I know the highest y value here? Absolutely I do. It's 4. That's my absolute max right there. Because I've restricted the domain from 0 to 2 for x. And x equals 2, y is 4, because y equals x squared. Just plug 2 in, that's 4, right? The absolute minimum is going to be 0. Again, easy peasy, nothing too challenging. Now these two I call half open intervals. Because half, oh sorry, my bad. I meant to say this one's half open. This is open because there's no bracket, but there's a bracket at 2 for the third graph. Let's change colors, let's do blue. So 0, there's a hole here, and it's closed at x equals 2. So that's what we call half open. It's closed at x equals 2, but open at x equals 0. Now, do I have an absolute maximum? Yes, I do. Still, it's a 4. But the absolute minimum, I don't know. So I say none again. It's close to 0, but what is it exactly? Like, you know, it's 0.00000000001. Like, I don't know. It gets infinitely close to 0. You know, it's just kind of this weird abstract idea. If I have two open endpoints, so I have an open interval, I don't have an absolute max or min. Again, it gets close to 4 for the absolute max, it gets close to 0 for the absolute min, but they're open, so I don't know. So what this tells me, this is a good lead to the next statement. What this tells me is that in order to guarantee an absolute max and absolute min, I must have a closed interval. You must have a closed interval in order to have an absolute min and max. And absolute mins and maxes are a very, very big deal in calculus. We're going to see that application flesh itself out later this week, next week, and even post-session. It's probably one of the most essential topics, especially in the free response portion of the AP exam. And there are practical applications. The crappy thing is that I can't cover those practical applications because it's post-session. I really need to talk about theory when we're here in person in this structured environment. The application stuff is going to be done post-session somewhat asynchronously. Kind of breaks my heart because I really wanted to cover that with you guys in this class. But we of course, had to slow things down last semester because I had to make sure you guys were getting the material. So anyway, it is what it is. But this is going to have some really cool practical applications you'll see later this spring, full absolute max and min. So in order to guarantee to find absolute max and min, you got to have a closed interval. Closed intervals are very essential here. Must be closed. Very, very important. Put a star there. That's how important it is. What also needs to be true? Well, notice that all these right here were continuous. So you're going to need continuity. That's another thing that's going to be important too. So let's look at the graph down below. Any questions so far before I move forward? Nope, okay. What also needs to be true is continuity, as I just mentioned. Like, let's look at this. This is closed from 0 to 6. You have a left endpoint that's included, a right endpoint that's included. Is there an absolute maximum value? No, absolutely not. The reason why is that it gets close to 4, but I don't know exactly. Like, see how I'm getting closer and closer to 4 here? But it's a discontinuity here. So here, remember, we have a jump. You might remember this from last semester. We have a jump discontinuity. Because we're not continuous, we're not guaranteed to get an absolute max. I do have an absolute min, but I don't have an absolute max. Question in the chat. Okay, if it was closed, then yes, you would. Someone asked, what if that was closed and this were open instead? Then yes, you do. But it's not a guarantee. Remember, in order to guarantee, we have to be continuous. So this is part of the extreme value theorem. Very important, putting a star here. I believe this is EVT, just so you know. So we'll just say EVT for short. If f is continuous, on a closed interval from A to B, we just kind of arbitrarily call the endpoints A and B, brackets are closed, then f has a maximum and a minimum on that interval. And when you say a maximum minimum, the default meaning is it means it's absolute. So sometimes some people omit the word. If the word absolute is omitted, assume it's there. Now, why do you care about that? I mean, aren't all maximums going to be absolute? Not necessarily. That's going to be on the second page. Again, we're quite a bit of theory going on here. Don't worry, we'll get to the fun stuff very shortly. Stuff we're actually going to do work. Okay, so that's extreme value theorem. If you're continuous on a closed interval, guarantee you're going to have a high point or low point, an absolute highest, absolute lowest. That's what this says. So let me clear my drawing. So let me just do another funky graph. So let's say I start at -2, and let's say the y value is like right here. And let's say I go down and up and like this. So I end at 4. Well, yeah, of course I have an absolute max right here. There's my absolute max. Do I have an absolute min? Obviously got an absolute min. Right there. However, things could look like this too. They could totally look like this. I could, let's say I have -2 and 4 again. I'm just randomly picking those numbers just so you know. Let's say it does some sort of like wavy stuff like this. So again, just being kind of oh goodness, undo. Now this is my absolute min, and that's my absolute max. So they can happen at endpoints too. Now, one thing that I want to ask, I'm curious to see, just get a kind of quick heat check here. What can you say about the tangent lines? And actually, question in the chat. In the graph to the right, if there was a hole near what looked like the absolute max, would you know if the absolute max existed? Yeah, if there's a hole there, then there's no absolute max. Yeah, if we had a hole here, someone asked about that, there's no absolute max. You gotta be continuous. You can't have any breaks in the graph. You gotta be smooth and, well, not smooth, because you can have corners, but you can't have any breaks in the graph. Now, just a quick heat check, and you can put in the chat, what is true about the slopes of the green lines I just drew? So I remember I drew them at where the absolute mins and maxes were. So just put in the chat, what's true about those slopes of the green lines? They're 0. Good. The horizontal lines. So that's going to be very, very important. That is like the essence of this week. Is the derivative, when derivative equals 0, you potentially have a min or max. The reason I say potentially is that you might have something that's a bit stationary that kind of sits for a little while and then keeps increasing, or it kind of goes down, sits for a while, and then keeps decreasing. We're going to explore all that later this week. But when the derivative equals 0, so that's why this is an application of the derivative. You take the derivative, you set it equal to 0, and we start working through it. We're going to do that later today. Yep, definitely the slope is 0. Thank you for those who contributed. Okay. So next page. Note that we can use extreme values as a blanket description for max or min values. So what's meant by that is that when we hear the word extreme, you think of highs and lows, right? And in addition to absolute max and mins, we have something called local or relative max and mins. We're going to talk about that heavily on Thursday. Thursday, we're going to have a heavy discussion on local local extreme values. Right now we're talking about absolutes. But a local, it's kind of like saying it's a higher, it's a, what's the right way of saying it? It's higher than the y values nearby. Or local means it's smaller than the y values nearby. We'll give you kind of a good example. There's actually one area in Redwood City that I drive by often. Someone, it's actually an old friend who just sold his house. He moved to Arizona. And it's actually a cigar family bought the house. I don't know who, but the house sold. I mean, I'll just kind of say it. I mean, the house sold for about $2.8 million. So it, not cheap. Now, is that the highest price in Redwood City? What'd you guys think? Probably not. I mean, there's some homes in Redwood City that sell for probably $3 or $4 million. But in that block, in that area that I tend to drive by, that is probably one of the highest priced homes. So that I would call a local max in Redwood City. I wouldn't call it the absolute max. The absolute max might be somewhere in Emerald Hills. Maybe Woodside counts as, Redwood City sometimes, right? Because that's the same zip code. And some of those homes are even more expensive. So within that neighborhood, you probably have one of the most expensive houses because it's sold for quite a bit. But it's not the absolute. It's not like, considering all of Redwood City being like, the whole domain. So an absolute, so local just simply means you're looking at things that are nearby you. So I'd call this like a local max. Because if I kind of focus on maybe from here to about like maybe here or so, that looks like it's the highest y value for a certain moment. But if I keep going, then I get higher y values afterwards. I know it seems kind of weird, like how do you know when to stop? And I'll kind of give you a little bit of a teaser of what we're going to see on Thursday. A local max happens when the slopes of tangent lines change from positive to negative. That's what we're going to talk about often on Thursday. Notice if I drew a tangent line right now, positive. Draw it afterwards, negative. So there's a change at that horizontal tangent right there. We have positive tangent lines, then 0, and then became negative. We call that a local max. Local min is going to be the other way around. We'll call this the local min right here. And a local min is when the slopes, and you guys know what I mean, slopes of tangent lines, I won't write that again. The slopes change from negative to positive. So yeah, here you have negative tangent lines, a horizontal, and then a positive. So like it's kind of like a roller coaster. You go down, then you kind of level off, then you go up again. We call that a local min. It may not be the lowest possible y value in our domain, but it looks like a low point nearby. Kind of like, again, like what if like, there's a house that sold for maybe $1.2 million in Redwood City. Oh, that's probably the cheapest home. Well, maybe let's look at other parts of Redwood City. Maybe other parts that are, homes are not as expensive. But maybe in that neighborhood, it seemed like the lowest priced home. So that's what's happening there. Now, here's a question. Will an absolute minimax also be? Yes, it will be. An absolute minimax can also count as a local minimax too, because it follows the same definition that I just defined for you right here and right here. And this is going to be, I'm really going to drive this home on Thursday too. We're going to talk about this a lot. But over here, we could probably call this an absolute max. That looks like the highest point, right? Endpoints kind of have their own kind of thing. And we'll talk about endpoints in just a little bit. Actually, I'm going to save that for Thursday about endpoints, about whether those are local mins or maxes. We'll save that for Thursday because I don't want to overwhelm you with too much stuff. So more formally, f of c, we call that c could be some x value. Like you can see we use like c right here. Here I use d. F of c is a local max if it's bigger than y for some open interval that contains c. So like maybe from like a to e, let's say. Say I did that open interval from a to e. Yeah, we say f of c is like a local max. Or a local min, maybe from c to d. If I focus from c to d, then, oh, that should be e, by the way, because we use e right there. Well, anyway, you get the point. It's all arbitrary with the letters you use. But yeah, you call that local min. Sorry, I meant the point over here. If it's lower than the other y values within that region. Now, this example here, I think is really confusing. Let's cross it off. I don't want to kind of explain what's happening here, but I don't really quite understand what's happening there. So I kind of do, but it's just kind of confusing. Let's just cross it off. Because I want to get to some, a little more theory and then get to some examples here. Okay. Page 3. So looking back, or just thinking about it, and I know we didn't do example 2, but where can we find local extreme values? At endpoints. And something that I'm going to call critical points. Critical points are when your derivative equals 0 or your derivative does not exist. And we're going to have that discussion down below. But we call those critical points. And can you have a local extreme value at a point C in the interior of the domain where f prime C is greater than 0 or f prime C? No. Your derivative has to be equal to 0 when you're in the interior of a domain. So let's say here's A, here's B, you have your endpoints. Okay, so you have something like that there. In order for this to be an extreme value, you need the derivative at C to equal 0. Or you can make it a cusp, as we see over here. You might remember cusps from a while ago, or a sharp corner. But you cannot have the derivative be positive or negative at that value and expect it to be a local extreme value. Extreme values must happen at endpoints or where the derivative is 0 or does not exist. So this right here is kind of also the essence of this lesson today. Extreme values, local and absolute, occur at endpoints or critical points. Again, a critical point, we call it critical because it's important, when f prime is 0, f prime does not exist. And it's also defined right here again as well. So let's have that discussion with these graphs down below. Then we'll do an example. Okay. Now, it is possible, however, that f prime could equal 0, and it's not a local min or max. All I'm just saying is that local mins and maxes occur at those places, but just because f prime is 0, it doesn't mean that it's going to be a local min or max. Also, it's possible for f prime to not exist and still not be a local min or max. So let's look at these points right here. Here, f prime is going to equal 0. Here, f prime is also going to equal 0. Here, f prime won't exist. Does not exist. Let me write that a little more neatly. And here f prime does not exist. Now, why is the derivative 0 over here? Because you have a horizontal tangent. Horizontal tangent. Here you have a vertical tangent. Here you also have a vertical tangent. Remember, we called this a vertical tangent right here back in the day. Remember, we called this a cusp. That's because the left-hand derivative did not equal the right-hand derivative. In fact, I think the left-hand derivative was positive infinity, and here it was negative infinity, so those didn't equal each other. Here, I think they're both positive infinity. That's a problem, you know. Obviously, you have horizontal tangents on the first two graphs. Horizontal tangents here and here, you know. But yeah, you know, you may not necessarily have a local min or max when f prime is 0. What really has to happen is you need f prime to go from negative to positive or positive to negative to be a local min or max. We'll have that discussion on Thursday. But just so you know, just because the derivative equals 0 doesn't necessarily mean it's going to be a min or max. And I'll show you how to actually verify that when we do the examples on the next page. And if we read the blurb on the bottom, I don't want to move the screen yet, but it says, however, if there are local max or min values, we'll only find them at critical points or endpoints. So that's where we look. So we look at endpoints and critical points. Critical points are when the derivative is 0 or does not exist. So in this case here, we definitely had a local max. And here had a local max. But here had no extreme values here. And here I also had no extreme values. So the first and third graphs had no extreme values, even though the derivative was 0 for the first graph and the derivative did not exist for the third graph. For second and fourth graphs, the derivative was 0 for the second graph, the derivative did not exist because there's a cusp for the fourth graph, and we have local maxes. So just something to keep in mind. Okay, now we're ready to do an example, and this is how the worksheet's going to look. You're going to be doing this stuff on the worksheets and in the homework you'll do for tonight. And our timing's looking good. This is kind of where I want to be right now. This is perfect. Maybe what we'll do is, we'll see how example 4 goes. If I have time to squeeze in example 5 before, I want to give you guys a break at 10:20 because you guys, we've been at this for quite some time. And I always will give you a 10-minute break. Just, you know, every, 2-hour classes all the way through just doesn't make sense. So I think we need a little break. So use analytical methods to find the extreme values of this function. So it's actually a 4-step process. Step 1 will be state that EVT applies. Step 2 will be to find f prime, set f prime equal to 0, and solve for x. This whole process is going to be finding your critical points. Step 3 will be to make an XY table using the x coordinates of the endpoints, of domain, and your critical points that you found in step 2. Remember, the critical points are found in step 2. And then finally, step 4 is a final statement about absolute max and min. this is a 4-step process. You got to tell me the EVT applies. You got to, and then step 2 is more analytical. Find f prime, set equals 0, solve for x. Step 3, make a little table. Use the x coordinates and endpoints and the critical points. You're going to plug it back into the original function to see, which y values are higher and lower. Then you make a statement. So let me walk you through this process right now for this example. I'm going to do this as a text box for step 1. So step 1, I'll do right here. I'm going to do it as a text box right here. Since, just give me a second, I need to type it first and you'll see it. Since f of x is continuous on the closed interval okay, you just see it in red in the lower left corner. You have to make that statement first. Since fx is continuous on the closed interval from 1 to 4. Now, how do you know it's continuous? Graph it. Graph it. That's how you know. How do we know just go to Desmos and graph it. You'll see for yourself. I know it's really a really weird function, but just look at from 1 to 4. You'll see it's continuous. It's nice and smooth. So, or it doesn't have to be smooth. It could have corners, but it's just it's continuous. So that's step 1. Check. Step 2. Find your derivative. So this is the fun part. Before I get too carried away, let's write this as 4 times x in -1 power plus natural log of parentheses x squared. Now let's take the derivative. -4 times x in -2 power plus 1 over x squared times the derivative, the answer, remember chain rule, right? Times 2x. Don't forget chain rules. All the old stuff is going to come back to you guys pretty quickly. -4 over x squared plus 2 over x. And you're going to set it equal to 0. Now you got to do a little algebra. Maybe one of the fractions over to the other side. Maybe I'll cross multiply. 4x equals 2x squared. Do a little more algebra here. Factor out 2x. So you get x equals 0 or 2. Those are your critical points. So that's step 2. You got to do the derivative, set equal to 0, solve for x. That will probably be where you spend most of your time, is my guess. Any questions about how I did that derivative or the algebra I did to solve for x? More than happy to re-explain if you need me to. Okay, let me go ahead and cross off, however, 0. Why am I crossing 0 off? Why am I going to throw it out?
Because it's outside of the domain.
Yes, it's outside the domain. My domain was restricted from 1 to 4. So sometimes you have to throw stuff out. 0 actually, just so you know, made the derivative undefined. Really, that's what it did, because you can't divide by 0. So the derivative would not exist there because of the discontinuity. However, we did a domain from 1 to 4 because we want to be continuous. Remember, discontinuities also lead to lack of differentiability or derivatives not existing. But we're focusing from 1 to 4. Okay, step 3. Step 3, you're going to do a quick XY table. you can use the coordinates of the endpoints and the coordinates of your critical points. So my endpoints are at 1 and 4. My critical point, I'm going to use 2. And you plug it into the original function. We're going to use the original function here. I'll kind of spare you the trouble. If you plug 1 in, I think you get 4. If you plug 4 in, you get 3.77. Just trust me on this. If you plug 2 in, you get 3.38. Okay. So that's step 4. Sorry, step 3. And then finally for step 4, I'll do as a text box, kind of a little white space here. And let me do a different color so it kind of stands out. I'll do it in a forest green. You make your final statement. F of x has an absolute max of 4 at x equals 1, and f of x has an absolute min of 3.38 at x equals 2. And let me just size this just a little bit. Okay. You should see it now. That's step, whoop, let me change colors again. That's step 4.
Mr. E.
Yeah, good.
So then what is the 3.77 value? Is that like a local max or min? Does it matter?
Actually, great question. We're gonna have that discussion on Thursday. Technically, let's actually look at the graph. So first of all, yes, this is an absolute max right here. That's an absolute min. And if I do a quick sketch over here, you know, x equals 1 had 4, right? X equals 4 had 3.77, which is probably over here. And x equals 2, we had 3.38, which is like maybe down here somewhere. So the graph kind of looks like this. Technically, we call this a local max. That's because the slope of the tangent lines before we got to that right endpoint were positive. And so they increase up to that point. But that's a discussion we're going to have on Thursday. I don't want to overwhelm with too much stuff. So we'll have that discussion on Thursday. But yes, technically you call that local max. Whereas if it's diving down to it, like say you do something, like say this is the lowest possible point, and you have something kind of like this here, then we call that a local min. So for right endpoints, if the derivative is negative before you get there, we call it, and it's all reversed for left endpoints too. But all that stuff, I'm just gonna save for Thursday, because this is the first time you guys have done this kind of math in a while, so I don't want to overwhelm you with too much stuff. Okay, so let's do a break. Example 5, maybe we'll hold off on that. Maybe that might be good to kind of talk about tomorrow. But we're going to do worksheet 1 when we get back from the break. So it's 10:20 right now. Let's come back at 10:30. I'm just going to turn off my video because I'm going to make Smoothie could hear the Vitamix. I don't know, maybe I'll leave the microphone on. Yeah, we'll come back in 10 minutes and then we'll talk. We'll put you guys in breakout rooms for worksheet number 1.